Today we'll continue specific analysis techniques. As I've been telling, these techniques are not meant for every circuit, specific technique for specific circuit. That's why I named this as specific analysis techniques. And we have already discussed about 5 theorems. All the 5 theorems linked to one theorem, that is mainly Thevenin's theorem. So we are going today all other remaining 5 theorems and also star delta transformation called impedance transform and transformations and source transformations also will be discussed here. With that we'll be completing this topic called specific analysis techniques. So let's go to details. The first theorem under which we are going to study today is superposition theorem, reciprocity theorem, substitution theorem, compensation theorem, and Teligand's theorem. In fact, some people even do not know that there are 10 theorems. So 5 theorems we discussed earlier. Now we are talking about 5 theorems. Let's go to one theorem by theorem, and that will be illustrated with a problem. Preferably that problem which already came in the previous exams, GATE exam or IES exam. If they are not there anyway, we have formulated our own problems to give the completeness to this topic. So it doesn't matter whether we chose problems from previous question papers or from some very good books or our own problems. The whole idea is to illustrate them and make you ready for the exam. So let's go for first theorem in this lot, superposition theorem. Let's see the statement. As I've been telling, in every theorem one should know the conditions under which the theorem is valid. So in a linear circuit with more than one source, the overall response across an element is the algebraic sum of responses due to individual sources acting alone. So let me explain what the definition is. Actually, in this statement you can add one more small tag. Those individual sources are added to the circuit at different timings. For example, you imagine your own house. Today you have one tube light, tomorrow you will have another tube light. That means load is getting changed. Today you have one source, tomorrow you have another source. Source is also changing. So when we will always, as the load is changing, we will always introduce sources one by one. So the previous source current is already calculated. So we don't need to calculate that previous current which is already calculated. We should only calculate this source and the current due to this source. So overall current is algebraic sum. Please understand, wherever we use the word algebraic, it means polarity included. It is a polarity that is included to talk about this. So we are going to calculate individual. What is the condition? As I've been saying, circuit should satisfy the linearity and homogeneity property. Linearity means two different things added. Homogeneity means it's also addition, but the same thing, same. So if the two different things are added, output is also added. That's called linearity. Two things, same things are added, output is also added. It's called homogeneity. The second condition is circuit is a bilateral. Actually, this word is optional. I have included this because some people give one source in one side and other source on the other side. When this source is considered, current flows in this direction. When this source is considered, current flows in the other direction. Therefore, current should flow in both the directions. Okay. So that's how I have considered this condition. And it's also said optional because most of the time people will be adding the source at the same terminal. Therefore, they they can be unilateral, not necessarily be bilateral. Third point, more than one source existing. As already said, not only more than one source, those sources are introduced at different timings. If all the sources are existing at the same time, we don't call it like that. We don't need a superposition theorem. You can as well do by mesh analysis or KVL and KCL. That's why superposition is basically not for examination, but it's more for industry. In industry, we have to add the sources all together. When we add the sources one by one, each year we will be adding or each month we will be adding. That's a general procedure in industry. Then, used for calculation of voltage and current when sources are introduced at different timings. This is what I meant. If all are introduced at the same time, examination is conducted at the same time, we don't really know this. We don't need this superposition theorem. We can directly do mesh and nodal. That's why my suggestion is, for objective exam, even if the question comes, two different sources are given, you can straight away go from KVL and KCL or mesh nodal. You don't need anything like superposition in the exam. But in IAS exam, like conventional exam, if they are asking different timings or using superposition, you have to use only superposition theorem, though the time is the same. So never go for superposition theorem in the objective exam. If they don't, only in the conventional exam you go. Even in objective exam, if they say using superposition theorem, nobody knows what technique you have used. You can directly use whichever is the shortcut for you. So that's why the problems, calculations and numericals are very less, but the condition and concept based questions are more in this. So that's all about superposition theorem. Look at here. If the input to the network is x1 and x2, then the corresponding output from the network is y1, y2. If both inputs are added, both outputs are added. That's called linearity. If 2x1 is 2y1, it's homogeneity. Once a student came to me and said he wants to write this 2x1 as x1 plus x1 and 2y1 as y1 plus y1, and he wants to argue with me that it is a linear. The reality is, it's not linear, because as I told, linearity means linearity and homogeneity both are addition. If two different things are added, it is linear. If same thing is added, it is homogeneity. Therefore, superposition theorem demands a condition for linearity. That's the condition we have. This is the network. Input is here, output is here. Let me illustrate with an example. Obtain the loop currents in the circuit using superposition theorem. Say for example, this is a loop 1 I1 and I2, R1, R2, R3, V1 and V2. Our understanding is V1 is here. For example, it is created in January and this is given in February. Do analysis with V1 in January and do analysis in February, then add them up. So that's the meaning of the word superposition theorem. Now let me illustrate the whole procedure. Now put in the first case V1 acting alone. That means this voltage source is 0. Please understand here, if it is a current source, we will make it as open circuit. So voltage source is acting as short circuit and current source will be acting as open circuit. We will be considering one by one. So apply loop equation here, solve for I1 and solve for I2. Keep them ready. These are the ways that we can really do it. Then case 2, put V1 0, work out upon V2. Again apply, call this as I3 and I4. Apply loop equations. I am not really telling them because it is a very simple. Now after so many lectures you understood, it's very easy now. But the whole idea of this concept is, what is the overall current? Overall current of I1 is, the loop 1 is I1 of the previous, I3 of this. Overall current of the loop 2 is I2 of the previous, I4 now. So loop 1 current is I1 plus I3. and I2 plus I2 plus I4 is loop 2 current. I give a small suggestion to you. You can repeat the same problem using mesh analysis and same currents will come. So when you go for mesh analysis, when the same currents are coming, you can decide which is very faster. But therefore, this is another way of solving a problem, and it is specifically used when there is more than one source, and those sources are created under different timings. Now let me take you to applications. It is used in linear circuit applications which has more than one source. This is the meaning of applications and theorem. Let me take you to the second theorem called reciprocity theorem. Okay. Statement. In a linear and bilateral network, the ratio of response to the excitation is remaining same even though the position of the source and the load are interchanged. So this is the statement. Let us see the conditions and understand this. The meaning is simple. The basic idea is reciprocal. It's a very interesting word. It's just like in everyday life we use say give respect and take respect. That's called reciprocal. When I give respect to you and you give respect to me, that's called reciprocal. So reciprocating each other is called the same theorem. What I mean is, when I give respect to you, I become the source and you become the load. When you give respect to me, you become the source, I become the load. Finally, the value is the same. That is what exactly happening in this theorem. So what are the things here? The circuit element should be reciprocal, linear and bilateral. Actually, the word linear, reciprocal itself, bilateral. Because as I said, give respect and take respect is two-way. It's a bilateral relationship. The circuit should not have any time varying elements. So if there is a time varying element, there may be that may violate. Third, it is applicable only for the networks containing single source. Suppose if you have more than one source, what will happen? You are interchanging which source where. That's why it's not like the previous one, it contains only one source. This source with the load here and source here, load there. That's exactly. What are the applications? This theorem should be used in antennas and transmission lines. The best example is antenna. The antennas that we use in our day-to-day life, it is always reciprocal. The best idea is to say, whatever the antenna that we use for transmission, the same antenna we use for reception. So for transmission and reception, the antenna is same. That's a very good idea. That's a reciprocal element. While transmitting one way, while receiving the reverse way. Another important thing you should understand, antenna is a bilateral, passive also. Transmission line is also same. Suppose you have a transmission line and a load. The best example is a telephone. The telephone impedance has to be equal to this, and the signal will go from this way, signal will come in that way. Particularly the transmission lines we talk about. Nowadays we talk about communication in duplex. Duplex means both ways. So therefore, when you are talking and sending the signal in both ways, it should be reciprocal. That's the meaning of second. So let me explain and this one by using an example. Verify reciprocity theorem. Please look at here very carefully. This is the source, that's the load. Now I will calculate current here. Let me calculate the current. This is the source, load is here. What is the current that you got? Simply apply VA minus 10 by 5, VA by 10, and then VA by 7 plus 3 means 10. So what is the value that you got for VA? 5 volts. Current through 7 ohm resistor. Very simple. That is nothing but VA by 10. So 5 by 10 means 0.5. So ratio of response to excitation is, response means IL, excitation means current, voltage, what you gave. So 10 by 0.5. The voltage is 10, the response is 0.5, the ratio is 20. And now you have a responsibility of showing the reverse order, and same 20 is coming. You need to show that. So please observe, I am going to case 2 now. When I come to case 2, please observe here, this was the source, actually I kept it here. Now come on, VA by 5, VA by 10, VA by VA minus 10 by 7 plus 3. That's again 10. If you calculate, you will get VA is equal to 5 by 2. If VA is 5 by 2, what is the current in 5 ohms? Current in this 5 ohms is 5 by 2 by 5. Current is 0.5. So what is the ratio to expectation now? 10 by 0.5 is equal to 20. So please observe, whether this way or that way, you got the same ratio. That's called reciprocity. So here you got 20. In the previous also you got 20. That's the beautiful idea called reciprocity. Now let me take you to third theorem, substitution theorem. When you say substitution theorem, let me give the statement. Any component in a linear bilateral network can be substituted by an equivalent voltage source with or without series impedance without any disturbing the network voltages and currents. Well, this happens many a times in industry. Suppose you are on the field. Think about a telephone man or any service engineer. He is going on the field. Most of the engineers on the field. When there are engineers on the field, when they go for really solving certain things, they found some element is lost. For example, 2 ohm resistor is lost. Then they don't have 2 ohm resistor to replace. What to do? They have to run the show. In industry, most of the applications, just for a small element being lost, the whole work is stuck up. And you should have an idea how to make the industry to work or how to make the system to move. In such case, you have to use this theorem. That's called substitution theorem. You can substitute the 2 ohms resistor, which is lost, by a voltage source. Suppose you have a battery in your pocket, you can just put it and see the work is done. But the condition is that battery should supply the voltage required. And that battery should be able to give the current or pass the current. So, current and the voltage should not be disturbed, but that voltage must be supplied. Then, though there is no 2 ohm resistor, it can be simply substituted. That's the meaning of substitution theorem. But look at here. I said by a voltage source. Then somebody asked me, why not a current source? And my answer was very simple. There is no current source in the world. Practically, there is no current source. Anybody uses current source in the place of, in the network analysis or anywhere in engineering, it's only for analysis. You can never realize a current source. Therefore, I wantedly, or we have to understand this one saying, you can put a battery with that voltage. If suppose the battery is not sufficient, suppose you need some 4 volts, you have only 2 volts battery, then what about the extra 2 volts to be substituted? You can use another resistor. So that drop may become totally 4. So that is the meaning of this substitution theorem. It's a very interesting theorem because with this theorem you can somehow see that system is going to work. So I'll give a small example. Suppose I am teaching. Suddenly I am bedridden. Then you have to substitute me with somebody else. But when you are substituting me with somebody else, the condition is he must teach the same style, same width and same depth. Otherwise we don't accept him. So same width means voltage, same depth means current. So, and in teaching also the same. We talk about width means syllabus, depth means question paper. If these two are satisfied, then only you can say you have substituted me by somebody else. That's the meaning of substitution theorem. Suppose if he does not bring the same width and same depth, we don't call substitution there. You are trying to do something, but you are not substituted. But another important thing, While when you are substituting me with somebody else, he can be X, Y, Z. It need not be unique. Suppose if you say you have to substitute with this unique thing, that is none other than me coming back and taking it. So substitution theorem or substitution is never unique. That's what you need to be careful. If substitution is unique, we don't call substitution. We call it bringing the same person and putting him. Right? There's a very beautiful applications in theorem in engineering. So let me take you to next theorem called compensation theorem. This is also very practical theorems. Let me read the statement for you. While measuring a quantity, measuring instrument is used, and every measuring instrument will have internal resistance, and that will create an error. Very interesting. See, when you are doing an experiment, and like a student I am talking, like for students, when you are doing some experiment, if you analyze with KVL and KCL, it will say 5 amperes will come. That's with pen and paper. But you want to use a measuring instrument and measure, what will happen? You don't get that 5, you will get 4.5. The reason is the meter that you have used for measurement will have some internal impedance. That internal impedance will create a problem, and that problem you need to solve. That's called compensation theorem. Therefore, to compensate error, the compensation voltage is created, and the actual current is algebraic sum of ideal current and compensation current. Please observe here again, algebraic means polarity. Now when you have what is actually we are going to do is, you will calculate the ideal current once for all. You don't repeat it again and again, because the value is already known to you. Theoretical value you call it, I call it as ideal current. But by introducing another meter, what's going to happen now? They will change. And every time, every instrument will create some error. So you don't need to calculate ideal current every time, only calculate the compensation current. In the process, you need to understand only, you take the algebraic sum, you will get the overall. So the beauty with this theorem is, ideal current is once for all calculated, but compensation current is calculated every time and the overall is estimated. Then we have one theorem called Teligans theorem. Actually, I like this to be called as a law instead of a theorem, because law is someone which is valid every time. You read the statement here. In any linear or nonlinear, time variant or time invariant, lumped or distributive is a network, the algebraic sum of all powers in all the elements is 0. That means Vn and In, because Vi is the power and this is number of branches. The algebraic sum, if you take, this is 0. Actually, in every circuit you can check this, but every time checking is a waste of time. So only once or twice we check it and enjoy this theorem, and that's why it is called Teligans theorem. Then if everything is valid, linear or nonlinear, time invariant or time variant, then what's the condition for this? The only thing to say, the network should satisfy the Kirchhoff's laws. It's very interesting. It is just like saying, as if no condition. Suppose you are applying for a job. Then people ask what the qualifications. Then he should be a BTech or should be a educated or non-educated, or BTech or MTech. Then somebody will say, no qualification. If he is a human being, sufficient. That's the best example. So Teligans theorems is as broad as that saying, if he is a human being, that means if it is satisfying Kirchhoff's laws, it is valid. So the only condition that we lay upon this is, Teligans theorem is, Kirchhoff's laws is valid. If Kirchhoff's laws is valid, entire networks is valid. That's why Teligans theorem is valid. So this is about it. We will go to problems and then let us go and see one by one how problems are being asked here. The first problem is concept-based concepts. See, questions are always two types: concept-based questions, calculation-based questions. Teligans theorem depends on law of conservation of charge, law of conservation of energy, both or none. See, as just now we studied Telegon's theorem, the only condition is Kirchhoff's laws must be satisfied. That means KVL and KCL. Kirchhoff's current law is based on law of conservation of charge. Kirchhoff's voltage law is based on law of conservation of energy. Therefore, Telegon's theorem is both. That's why answer is C. So this is what Telegon's theorem, first problem. Let's go to second problem. Superposition theorem is not applicable to a network containing time-varying elements, non-linear elements, time-invariant elements, none of them. As we discussed in superposition, the main condition for superposition is linear. Now the answer is, if you look at here, it is not applicable for non-linear elements. Answer is B. Non-linear. This is asked in GATE 94 EEE. Now let's go to third problem. Superposition theorem is not applicable to a net. Please understand, not applicable to a network containing non-linear elements, dependent sources, independent sources, transformers. So this is asked in 98 to 1 mark. As I've been telling, concept based questions are generally 1 mark. Calculations are 2 marks. Then what happens is, this theorem, again non-linear element is the answer. Answer is A. Non-linear element. So let's go to fourth question. Use the data given in figure A. Find the current in the figure B. This is very interesting. There is nothing involved much but understand. This is figure 1. This is figure B. Figure A, figure B. What is the basic understanding? He himself said, this is the voltage, this is the current. Now this voltage is brought here and this current should be brought here. For example, according to superposition theorem, what can happen is, if this 10 volts come here, it should be 2 amperes here. Therefore, answer can be 2 amperes if this is 10 volts, but now it is 20 volts. That means that should increase to 4. And polarity direction also, you see, this is the direction, so this direction is opposite. Because this is going in this way, whereas this is coming in this way. So that has to be minus 4 amperes. So answer is C. So very simple logic. There is no mathematics involved. You know why? Because even the component values are not given. So a student need not do anything. He indirectly gave an idea. But by looking at this, in the marks you see, 2 marks. 2 marks is very high. Because this is based on reciprocity theorem. If source and current are interchanged, that is the meaning here. That's why very good question, very fast. It takes only 1 second to answer, but gets 2 marks. That's the solution here. Now, which theorem is applicable for linear, non-linear, time variant, time invariant, active or passive? So this is basically given in IES, and so many things involved. You have none other than Telegon's theorem. Why? It's only Telegon's theorem which is applicable to everything. Only condition is, one important condition, as I said, only Kirchhoff's law should be satisfied. So answer is C, that is Telegon's theorem. Now let me talk to you. So far I discussed about specific theorems, specific analysis techniques. You have seen some theorems, but now I am going to talk to star to delta transformation. This is also called, star means like T, delta means like pi. So some people call it as T to pi transformation. So look at all this. The outer one is called pi. Inner one is like T. It doesn't matter, it is inverse one, doesn't matter. So how do we convert? Suppose you say Z1, that means pi. So how to get pi components from T components? That is nothing but When you want Z1, best way to remember is, what are the elements linked to this Z1? ZA, ZB. You multiply. Divided by third element. Then plus ZA, ZB. Now we look at the Z2. Z2 for example here. ZB, ZC by ZA. Then remaining other two you add. Z3, same thing I will show you. What is connected for Z3? ZA, ZC. And by ZB. Then remaining get added. So this is how ZA, ZB here, ZA. So ZA, ZB is multiplied, ZA, ZB is added. ZB, ZC multiplied, added. That's why I am just telling you how to remember. Then delta to star, reverse operation. When you go for the reverse operation, look at here. If you want ZA, Z1, Z2 by total. What are the things multiplied here? Z1, Z3 by total. Here, ZB you want Z1, Z2 by total. ZC you want Z2, Z3 by total. Very easy to remember. Let us go to the problems. You may think that such a small thing would not be asked in the exam, but they already been asked. So, a sixth problem. A delta connected network with its Y equivalent is shown. The equivalent resistances R1, R2, R3 in the ohms are respectively given. What I mean is, ohms is already mentioned. You don't need to mention the ohms in the answer. So he has given, what is given is delta for you. What is given is, what he wanted is T. Now you just put this T under this, you will understand. For example, R1. I am just telling you, R1, 5 into 30, 150. By total. Total is 60. So 150 by 5 into 30 by total is 60. So 150 by 60 is how much? 1.5. So see the example. Solution also I gave it here. 150 by, that's 3 ohms. 150. This is 50. It's not. So 150 by 50 is here. Then 15 into 5, 1.5. So the answer is D. So look at your ABCDs. Simply follow the option. Very small. Same circuit, same problem is asked again. That, but only thing is values are changed. So such a thing you can understand somehow. Sometimes people want to help you to pass in the exam and try to catch the small problems like this. Same example, same approach. 10 by 40. So 100 by 40, 200 by 40, 200 by 40. So the answer is A. So like this we can always solve a simple transformations, that is called impedance transformations. When you are going for impedance transformation, that is simply called star to delta, delta to star. Now I am taking you to the last point in specific theorems, that is called source transformations. What is source transformations? For example, the name itself says voltage source is converted into current source is converted into voltage source. That's the first idea. Second is series combination of sources, parallel combination of sources, same direction, opposite direction. All these things will be discussed under this heading called source transformations. Look at here. To make the circuit or a network simple, for easy calculations, source transformation is very helpful to us. Ideally, there is no current source and no ideal voltage source. But for every easy calculations, we may convert voltage sources into current sources and vice versa. You know what I mean by this sentence is, suppose when you are converting voltage source into current source into voltage source, I will tell you why ideal things cannot be converted. Look at here. we want to convert voltage source into current source and current source into voltage source. That's why I said vice versa. A voltage source with series impedance can transform to its equivalent circuit current source with shunt impedance. Look at here. This is Vs, Z. Voltage source and Z. Voltage source always impedance has series. Current source has shunt. For example, what's the conversion here? Whatever Z is here will come here. Will come here. I have a very important statement to say here. In a voltage source, we all expect Z to be small. If Z has to be small, and in a current source, we always expect Z to be large. Now, suppose this is 0. You are converting. If 0 comes here, what will happen? The total current will be here and here. That will not go to the circuit anyway. It will be simply here and here, nothing goes out. That's why, very interesting, if it is ideal voltage source, this cannot be converted. Suppose that's why this impedance, voltage source expects 0, current source expects infinity. Are they not contradicting? That's why practical sources can be converted. That's a meaning. Or sources with practical impedances, this is not ideal, so it's not 0. This is not ideal, this is not infinity. You can always convert them. That's the meaning. So that is how I have written this sentence called ideal things we cannot convert are meaningless to convert. Now let me show you. Two voltage sources in series can be converted into a single voltage source like this. Okay, V is equal to V1 plus V2. Please understand the polarities here, minus plus, minus plus. Both are here. Look at here, same series only, but one is minus plus, other is plus minus. That means subtraction. So this is addition, this is subtraction. So series voltages getting added. Then let me take you to two current sources are in parallel, can be converted into a single current source. How is it? I1, I2. So both are in same direction. That's why added. And one is the up and other is down. That means subtracted. That is also very interesting. You could see, you can check and subtraction. So here we take the difference, here we take the addition. That's the meaning. Suppose if two current sources are there in series, the least one comes. The least one being I2, they come here. If two voltage sources are in parallel, the least one exists. That means whatever the least one is V2, that appear here. This is how equivalent of voltage sources you can connect. And if you have voltage source and current source, you can have a equivalent of voltage with the current flowing and equivalent of current with the voltage existing. Then if you have serial voltage sources, so far we discussed about ideal, but now there is a resistances, they get added. If parallel current sources are there, current sources are added, and impedances is also parallel connection is taken. So you can simply say R1 parallel R2 is put across this. Now let me take you to the problem. For the circuit shown in figure, find out the current through 2 ohm resistor and also identify the changes to be made to double the current through the 2 ohm resistor. Look at here. This is a voltage source, the current source. There is a resistor here. Now what is happening is, we have to calculate in this how much current is available, how much voltage is available in order to double. So please look at the options here. 5 amperes, Vs is here, 2 amperes, 8, 5, 10. Like that we need to decide what is happening. Now let us see the solution. When a current source is in parallel with ideal voltage source, the effect of current source is emitted. Because it is in a parallel, that effect is omitted. Then what happens? Only the voltage source comes into picture. What is the current here? 4 by 2, 2 amperes. 2 amperes here. To make the response at resistor double to the voltage source is also we have to double. For example, if you want to double the current, resistance cannot be changed. Therefore, voltage must be doubled. So that's why the earlier is 4, now to double should become 8. So answer is 8 volts, 2 amperes. The option is B. So this is an example to talk about sources. Now I am talking about compensation theorem. Calculate I if the internal resistance of ammeter is 1 ohm. As I said, every measuring ammeter will have internal resistance. So inside this ammeter there is 1 ohm. So what to do? First go for practical. 20 by 3 by 5 by 3 plus 5 plus 1, which is inside. That's the actual value. That is 20 by 23 amperes. Next, ideal. Ideal means very simple. Assume this meter is ideal, 0 impedance. So 20 by 3, 5 by 3 plus 5. That gives 1 ampere. Now you can clearly see 20 by 23 is practical. This is 1. So ideal is more than practical. Why this difference is coming? This difference is because the measuring instrument is creating its own error. That should be compensated. That's why this theorem is called compensation theorem. Look at here. First I am calculating compensation voltage. The internal resistance of the ammeter, ideal value, that is 1 ampere, as we discussed, as we calculated in the case 2. So 1 into 1 becomes 1 volt. This is 1 volt compensation theorem. Now what is the compensation current? Very simple. Please remember, this source is removed. Original source is removed. So 1 by 5 by 3 plus 5 and 1. This becomes 3 by. So what is the overall value? Ideal is equal to I practical plus compensation. So what is the ideal value here? 1. 20 by 23 is practical. Compensation is 3 by. So overall is 23 by 23. Answer is 1. So this is how you really achieve. So the compensation only every time you have to calculate. For example, case 1 and case 2 is always standard. Only case 3 changes from measuring instrument changes. So that is the meaning of this compensation theorem. Now, let's go to the last problem. This problem belongs to substitution theorem. When you talk about substitution theorem, it's a 2 ohm resistor. I want to substitute 2 ohm resistor in the field, as I said. So as I said, if you are going into the field and 2 ohm resistor is spoiled, how do you manage? You can't say that element is not there, therefore I can't do it. So while substituting an element, it should contain the same voltage and same current. Otherwise, how can this work? So now, we are going to calculate different approaches. As I mentioned in the theorem, you can have only voltage source, but current should be same. You can have a voltage source in series with resistor and another voltage source in series with resistor. First calculate what is the current through this 2 ohm. Across this 2 ohm resistor, what is the current? Voltage. And what is the current through the resistor? Now I am just calculating very fast. You can see that. So simple, that's why fast. 1 plus 1, 2. 2 parallel to 1. 1 plus another 1, 2. 8 by 2 is 4. Therefore, the current in this is 4. And this 4 getting divided between 2 equal resistors. Why do I say equal? 1 plus 1 is 1, 2, 2. So, the current through this branch is 2 amperes. Now, please understand and calculate current in this branch is 2, therefore voltage across this branch is 2 into 2, 4. Good. Now what is your responsibility is, in every substitution between A and B, you should have 4 volts, 2 amperes. This is done. Now 2 volts is here and another resistor. What I said in the theorem was, suppose you need 4 volts. In your kit you don't have that 4 volts battery. What to do? You put 2 volts battery and remaining adjust with resistor. So come on and see here, 2 volts is adjusted, remaining 2 volts I am going to adjust with resistor. Very simply to say, you can apply KVL if you want. 4 minus R1 into 2 minus 2 is equal to 0. R1 becomes 1 ohm. Or you can simply see the total voltage should be 4, battery available is 2, so remaining that I should achieve is 1 ohm. So 2 into R1 plus 2 is equal to 4. So the total, therefore when you put a 1 ohm resistor, it is achieved. And thirdly, suppose if I connect this battery up reverse order, now what will happen? Just observe here, 2 into 2, why? Because current is here, 2 into R2 minus 2, okay, because minus is the direction here, is equal to 4. So what should be the value? 2 goes that side, becomes 6, 6 by 2 is 3. Therefore please remember all the 3 options. Here no resistor, here there is a resistance of 1 ohm, here there is a resistance of 3 ohms. So all the 3 are doing the job. All the 3 are having the same voltage. All the 3 having the same current. Having the same voltage and same current, they can do the job. That's why we call it as substitution. I can substitute this 2 ohm resistor by one of these 3. That's why I told you substitution is never unique. If it is unique, it's not substitution. So this is the meaning of substitution theorem. So this is how we can understand all the theorems. There are 10 theorems and each theorem has a specific application. So I named this as specific analysis technique. Along with that, at times we use source transformations and impedance transformations, voltage to current, current to voltage, and then we also discuss about star to delta transformations. All these 3 theorems and source transformations and impedance transformations I have brought into one slot called specific analysis techniques. By this time, please remember, we have finished the techniques required for the circuit analysis. Then in the next lecture, I am going to enter into applications. We have studied introduction to theorem, introduction to analysis. We have studied theorems, general analysis techniques and specific analysis technique. By this, in any subject, analysis techniques you should understand, but you should have applications in which you apply these techniques. So next lectures we will go for this analysis. We are left with only 2 topics. One is called time response, other is called frequency response. So with that, we will really complete this altogether. And then of course 2-port networks. So these 3 topics are applications that we will see in the next classes.